In this lesson, we'll take a look at making some connections between some fairly real-world data and modeling it using a sinusoidal function. And we'll also take a look at, in this example, of calculating an instantaneous rate of change for a sinusoidal function. So two examples. The one on this page says we have a Ferris wheel's height. Height depends on time here. It's written as a function of time. And it's given by this equation. The height is 12 times the sine of pi over 10. Notice that we have a pi here, so we're measuring the angle in radians, times t minus 5 plus 14. The height's measured in meters and the time is in seconds. And we're asked to calculate the instantaneous rate of change for the height at 6 seconds. Now, in order to calculate any rate, it would be the change in this variable, which is height in this case, divided by the change in this variable, which is time. We can make that look a little more like a slope calculation, writing delta h as h2 minus h1, the difference between two heights at 2 points in the graph, and the change in time is the difference between the two times associated with those two heights. Now, we're actually going to calculate a slope of a secant line, but we're going to take 2 points that are so close it's going to be a pretty good approximation for an instantaneous rate. So that's my abbreviation for instantaneous there. And so, since we're doing this for the instantaneous rate at 6 seconds, I'll make the h2 time 6 seconds, so we put 6 here. And I'm going to choose a point quite close to a time of 6, so we're going to use 5.9 for the second time. So the difference between these times is only a tenth of a second, 0.1 second, so it's going to be a pretty good approximation for the actual instantaneous rate at 6 seconds. Now, how do I calculate h at the height at 6 and the height of 5.9? Well, I use my formula up here. So in order to find h of 6, I'll put 6 in place of time. So there's my 6 in place of time. So it's 12 sine pi over 10 times 6 minus 5 plus 14. That quantity is the h of 6. In order to find the height at 5.9 seconds, then I'll put 5.9 there. So it would be 12 sine pi over 10 times 5.9 minus 5 plus 14. So what's in the square brackets here is the h, the height at 5.9, or the h of 5.9 value. In the denominator, we subtract the 2 times, so 6 minus 5.9 is going to give us a tenth of a second there. Now, how do we calculate these? Well, I'm going to go to my graphing calculator here. Now, so it's 12 sine pi over 10. There's the pi over 10. Now, 6 minus 5 is 1. So this actually just simplifies to 1 pi over 10. In the second set of brackets, 5.9 minus 5 is 0.9 seconds. So this would actually be 0.9 times pi. So there's my 0.9 pi over 10. Notice I don't have the 14s here because this plus 14, and then when you remove the square brackets here, will be minus 14. So you don't really need to write the plus 14 and then minus 14 in the end because that's going to be the same thing. So we evaluate that quantity, and we get 0.36. We'll go back to our... So the instantaneous rate is, or a good approximation for it, is going to be 0.3603 meters, and then of course in the denominator we have 0.1 seconds. So dividing 0.36 by 0.1, we get about 3.6 meters per second. And so that's a very good approximation for the instantaneous rate. It's pretty close to 3.6 meters per second. What that rate actually looks like in the graph, if we were to actually draw a tangent line in at 6 seconds, then the slope of that tangent line should be 3.6. Now, if you look really closely on the graph, it actually isn't 3.6 here. If, for example, if I go across 1, I'm only going up just under 3. So I don't actually have a slope of 3.6, but that's some of the limitations of drawing a graph with PowerPoint. Now, we could make that approximation better if we took a shorter time. And let's go back to the graphing calculator one more time. For example, if we made this 5.99, and then this would be 5.99 in the denominator, then the only thing that actually we would change is on the end. You see, if I did 5.99 minus 5, this would be 0.99 pi. So if I insert another 9 here, then in the numerator, I'll get 0.03587, etc. Now we'd have 6 minus 5.99, so the change in time in the bottom would be 1/100th of a second, 0.01 second. So if we divide that by 0.01, we still get an answer pretty close to what we got. 3.587, 3.6, they still round to a tenth to 3.6, so that is still a pretty good approximation. On to the second example. We're given that the moon is illuminated differing amounts depending on its relative position to the Earth and Sun, and we can see in the diagram as the moon revolves around the Earth, it's illuminated different amounts from the Earth and by the Sun, of course, and so we go everything from a full moon to a new moon. And the equation for a particular period of time is given in the table here, so we're going to graph this. So day 1, we have an illumination of 0%. On day 4, it's up to 10%. Day 8, it's up to about 50. Day 11, it's at 80%, and at day 15, it's 100. And then the other days, day 19 is down to 80 again, day 22 is 50, day 26 is at 8%, and then we're back down to 0% or a new moon. Now if we draw a smooth curve through these, we get certainly a sinusoidal shape. And one thing that's very useful here is I'm drawing this line right through the middle so we can easily see what the amplitude and any vertical translations we have are. So that's right through the middle, which of course 50% is exactly in the middle between 100 and 0. So the vertical translation, doesn't matter whether we're using a sine or cos graph, it's been translated 50 units up. That's the vertical translation. Now the amplitude is the distance from that middle axis or middle line to a maximum point or the minimum. So this is 50 or this is 50%, so the amplitude is 50. The period of this function is 28 days. It's 28 days from day 1 to 29. 29 minus 1 is 28. So it's 28 days long from here to here. Now, in order to model this, remember the constant in your sine or cos graph that goes right after cos or sine is 2 pi. Remember, 2 pi is a full period of a normal sine or cos function that hasn't been transformed, divided by the actual period, which of course in this case is the 28 days. So in order to get the k that goes in our equation, the k is 2 pi over 28. Our period being 28. And of course, 2 goes into 28 14 times, so the constant, the k value, is pi over 14. So an equation, actually I'm going to write 2, the percentage as a function of the day. Now, we could model this with a negative cos function. Remember, cosine normally starts at a maximum, goes down, has a minimum in the middle, crosses, and then back up. So this is actually a negative cos function. So we could model this with a negative cos function. This is where the constant goes. And there's a small phase shift or horizontal translation because this point isn't right on the vertical axis. It's 1 unit over. So that's the phase shift, moved 1 to the right. And then it's moved up 50. So that's the vertical translation, up 50. Another function we could use is we could model it with a sine curve. Remember, sine curves start right in the middle of that axis, go like this, and then of course end over here. We only see about 3/4 of a cycle here. And so the horizontal translation is 8 days, so that's why it's d minus 8. The rest is the same. The constant k is still the same, pi over 14. And so that's another function we could use. Now just to show you that that's a pretty good approximation, I'm going to go back to my graphing calculator here. And if I go into the stat function and edit, I have typed in this data, the 1, 4, 8, 11, etc., 1, 4, 8, 11, etc., and all my percentages here. And if I go back to the stat function, there's a whole bunch of regression equations in here. And the one I'm going to use is the sine. So this should give me, and I can tell it that it's in, the information's in list 1 and list 2. And it should give me this equation right here. So the a value is 50.1. Well, it's pretty close, so I've got to get 50 here. This constant here is actually the b value, 0.2267, etc., which actually, if I divide pi by 14, is pretty darn close, 0.224, 0.226. Okay? The c value here actually comes from factoring, this actually doesn't give it in factored form, the pi over 14 out. And so if I actually take the 8 and multiply it by pi over 14, that gives me pretty close to that number, 1.82, 1.795, etc. And then of course the translation is up 50.